Okay, this is Physics 1C for Thursday, April 30th. Today we're going to be talking about some more Faraday's Law problems to kind of discuss some of the details that you need to understand about how to solve them, and I hope that these will help you guys solve your homework. I looked at our homework and we're doing really well in terms of like content. Like we're really far ahead. The homework for Faraday's Law isn't due until May 15th, which is 2 weeks from now, and this is pretty much the last like lecture on it. So, you know, we're really far ahead as far as the content goes, but if you guys are still getting behind on homework, I understand. Okay, let's talk about how to solve some of these problems here. I really should have moved this stuff down before class. Here, fix the stuff real quick. Just pull this one off to the side. Same thing with this. Alright, okay, let's get started. So this is the problem I want to start with. There's a lot of words, so I'm going to read it and we'll talk about it. This picture is the picture that goes along with it. As a summary of like what we've done before, Faraday's Law is a statement about how you can get what's called induced EMF, and the statement is basically that the EMF that's induced in a coil is related to the negative of the number of turns on a coil multiplied by the time derivative of the magnetic flux. So a whole bunch of symbols that, you know, you look at that equation, it might not mean much to you, but the idea is that magnetic flux can often be written like this, as just, you know, magnetic field times the area of the loop times the cosine of the angle. So I feel like this equation is it's pretty hard to just conceptually understand, but it basically states that moving a magnet near a coil will induce current in it, or changing the magnetic flux through the coil will also induce a current in it. Okay, so here's the problem. We've got this setup where we have a current I that's flowing here through this set of loops and coils that are wrapped around this core. We have another coil, you can't see that thing on the screen, but this right here, this little copper looking thing, is surrounding it. And it says an aluminum ring with a radius of 5 centimeters and a resistance of 3 times 10 to the negative 4 ohms is placed around one end of a long air core solenoid with 1,000 turns per meter and a radius of 3 centimeters. So we've got these values here, right? You can see them in the problem, but I think it helps to write them up here. R1 is equal to 5 cm, and R2 is equal to 3 cm. We also know that the ring is aluminum. I can't remember if that matters or not. But we also know that the resistance of this ring here, R, is equal to that number right there. Big R is going to be our resistance, the electrical resistance, and that's 3 times 10 to the negative 4 ohms. And it also has a total of 1,000 turns per meter. That's to say the solenoid. This one right here has 1,000 turns per meter. The symbol for that is the symbol little n. What is it, 1,000? Right? It says, assume the axial component of the field produced by the solenoid is 1/2 as strong over the area of the end of the solenoid as at the center of the solenoid. Also assume that the solenoid produces negligible field outside its cross-sectional area. The current in the solenoid is increasing at a rate of 270 amps per second. What I'm going to call that is, this number is effectively the rate at which the current is changing. So we can call it whatever we want to, but I'm going to call it the kind of the derivative of the current. It's the rate of change of the current is 270 amps per second. The first part says, what is the induced current in the ring? That's the first thing that we're going to try to figure out. And then some other things. Okay, this problem is really long. It's also similar to your problem you guys have in your homework. So I just want to kind of address it and make sure you understand the details of how we do it. So does anyone have any questions about this so far? Okay. So I guess we'll just start with this to see how much you guys remember. What is this thing going to be used for? And to be clear, that's the number of turns per unit length, like in these wires here. like if this thing was 1 meter long, right? If it was 1 meter, then there'd be 1,000 turns in there. If it was 2 meters long, there'd be 2,000 turns in there. Turn is one wrap around the thing. Why do we need to know this piece of information? What can I use that for? Can we? But we don't know how long the cylinder is. Wait, what is it you said? It's all for big what? Okay. Well, again, we need to know the length, but I want to be clear here, by the way. This N, so I'm glad you said that, this N represents the number of turns in the object that is having the current induced into it. So that would be the number of turns in this guy, which there's only one, because it's just a ring, right? Does that make sense? That big N there, in this case, is just going to be equal to 1, unless I misread it. It just says, yeah, it's an aluminum ring, has a radius of 5 centimeters, and this resistance. It doesn't tell you that there's any number of turns in it, so N is going to be equal to 1 here. Okay, that was a good guess, though. What else could we use it for? Do you guys remember any equations where that shows up? Yeah, that's right. There's an equation that says that if you have a solenoid, and this thing is a solenoid, just to remind you in case you don't remember or haven't spent much time reading about it. A solenoid is this object that has these coils that are wrapped around a core like this. And the magnetic field for a solenoid is equal to, like this. It's like mu naught, the magnetic permeability constant, times the number of turns per unit length, multiplied by the current that flows through it. So this solenoid, and what I want to do is I want to kind of like look at it from this end. Like if you're looking in this direction, what we would see is we have this solenoid, and we'll just use like black to represent the core of the solenoid. The solenoid is wrapped with all these coils. And how are they wrapped? Well, they're wrapped kind of like in like a way like this. And the current that's in this flows basically this way and then this way and kind of around like that. That's your current. And if the current flows that way, it's going to produce a magnetic field inside the core of the solenoid that points kind of into the board like this. That's the magnetic field. I feel like I should just like kind of, what this good if I just expand it a little bit. All right. So the magnetic field inside the core looks like that. That's the magnetic field of the solenoid right there. But then we have this ring that's wrapped around it, right? Okay. This is the ring here. Like this corresponds to this. So that's our kind of our picture there. We could even draw it maybe without the. Really, what we've got is basically a situation like this. I've got two rings. Yeah, let's make one of them red. Oops. Shapes. Let's make one of them red. We'll make the other one blue. Oops. I have to click here first. There we go. Shapes. No shapes. Click. Blue. Shapes. Click. Will this allow me to do like that? Yeah, okay. So this is basically what we have. You've got your outer ring that has a radius that we're calling, I think, R2, right? No, R1. You've got your inner ring that has a radius R2. And then you've got your magnetic field. And it's going into the page like this. All right, so we can find the magnetic field of the solenoid with this equation. And knowing that we know that, right, we can now say that if I want to find the induced EMF in this loop here, the question is, what's the EMF induced here? then what I have to do is basically use this equation, right? So let's kind of put things together here. So our EMF that's induced in the outer ring is going to be equal to -1 times the time derivative of the magnetic flux. The magnetic flux is going to be given by B times A, and then in this case, the angle between the magnetic field and the area vector, I would say that the area vector in this case is also pointing into the page. The area vector is the area vector for this blue loop right here. I guess we can use blue to represent it. But that area vector is going to point, into the page. We'll just label this as the area vector. That looks awful. I'll just do it like that and say that the area vector points into the page, which means that we're going to be doing BA times the cosine of 0. And this is going to be the magnetic field of the solenoid. With one caveat, which is in the problem, it says that assume that the axial component of the field produced by the solenoid is 1/2 as strong over the area of the end of the solenoid. What that means is that the magnetic field that I'm drawing right here is actually 1/2 of the magnetic field of the solenoid. So I have to put divided by 2 here. Just because of that, what they say, 1/2 is strong. All right. So then, I'll stop for a second. I feel like I said a lot of things. Do you guys have any questions? Okay, so which area are we going to use then? Is it going to be the area of the outer circle or the area of the inner circle? Why is it the inner circle? Or how do you know that? So you're kind of saying like the magnetic field here is 0, right? Yeah, in this region the magnetic field's 0. That's where it says assume that the solenoid produces negligible field outside its cross-sectional area. So in this region we're saying B equal to 0. So the flux is really only through, I'm going to draw some extra lines here. The flux is really only through this area here. Okay, so the flux is going to, or the area is just going to be pi times, I think, R2 squared. So we're doing only the area where the magnetic field actually is. So now we're doing the time derivative. Let's start putting things in. The magnetic field of the solenoid divided by 2, right? So that's mu naught. The number of turns per unit meter. The current flowing through the solenoid, all of that divided by 2. And then now we have to multiply by the area, which is just pi times R2 squared. And we have to take the derivative of all of this. Luckily, almost all of these things are constants. Pi, mu naught, n, and R2 squared are constants we can pull out. So we get negative mu naught, n, pi, R2 squared, divided by 2, and then multiplied by, the only thing that changes in this problem is the current flowing through the solenoid. So then just ddt of the current is left. And we know what all of these things are. They're all right above kind of this line right here in terms of the given information. And we can just plug them in. Oops. Okay. Do you guys have any questions before we plug things in here? Yeah, let's go over this way. So mu naught is 4 pi times 10 to the negative 7 Tesla meter divided by amp. Multiplying that times n, which is 1,000. Times pi, R2 squared. R2 is 3 centimeters. all divided by 2. Oh, and we need to multiply by di dt, which is 270. This is going to give us the induced EMF. This isn't even the answer, though, because we actually have to divide by the resistance. I suppose we could do that, but let's get the induced EMF first, and we'll find what the... Can you guys calculate what that is? And tell me what you get? I'm out of water. While you guys are doing that, I'm grabbing some. Anyone get an answer? That I kind of like lose you guys? I know this problem is really tricky. I know all of ENM is pretty tricky. Were you guys able to get an answer, though? What did you get? You can type it in the chat. It's a lot easier than saying it out loud, but if you want to say it out loud, go for it. What'd you get? Okay, I'm going to calculate too. Okay, you answered the current. Did you get 4.8 like 0.48 millivolts though for this answer? I think that's going to turn into what you wrote there. This is what I got. I got 4.8 times 10 to the negative 4. This is going to be in volts. Does that look right? And that would give us then, if we want to find the current that's induced in the thing, oh, there's a negative sign here, we'll talk about that in a second. If you want to find the induced current, that's going to be equal to E over R. So that's going to be equal to just E divided by R, which is right here. So if we just take that number and we divide by 3 pretty much. I got 0.16, Hunter, amps. That can't be right. Oh, times 10. 1.6, yeah. I only multiply by 1,000. 1.6 amps. Is that what you got too? All right. Yeah, there's a negative sign here. What do these negative signs mean? Well, they mean this. Our current was flowing this way before, right? We'll use red. Red's fine. The current is flowing this way. I thought that was going to be red. The induced current has to be the negative of it, or the opposite direction. So the induced current is going to flow this way. Sorry. That's the induced current. Does that make sense? Had, the current was increasing, right? So if the current was decreasing, then you'd have a negative sign on that, and then your induced EMF would be positive, so it would be in the same direction. Does that make sense to everyone? Okay, we've already asked, well, we haven't quite, but we've almost answered part C. So part B says, what are the magnitude and direction of the magnetic field produced by the induced current in the ring? So the fact that there's an induced current in this blue ring right here also means there's going to be a magnetic field produced in that ring, right? And in particular, it's going to have a magnetic field at its center that we've calculated before. So if I have my ring like this, and I have a current flowing in this direction here, you guys maybe just tell me, what direction is the magnetic field at the center here? Does it point into the board or out of the board? can use the right-hand rule. So the magnetic field inside of here is going to point like this. And we can calculate what it is because it's a ring and it has a radius that we're calling R1. So the magnetic field at the center should be equal to mu naught I divided by 2 pi times R1. We derived this using Ampere's law recently. We derived it using the Biot-Savart law about 4 weeks ago. But this is the magnetic field at the center of a circular loop. And the current in this case is going to be the induced current, I should say. So this should be equal to mu naught is 4 pi times 10 to the negative 7. The induced current is 1.6 amps. We're not going to put a negative sign in here now. And, 2 pi. I think R1 was 5 cm. And that would be 0.05 meters. What's this going to be? 0.05. It's like 1 over 20, so times 20. I feel like it's going to be like 64 something. Probably like this. I don't know. What do you guys get if you calculate that? That was close. And Tesla is the unit for the magnetic field. Okay. Does that all make sense to everybody? Does anyone have any questions? Okay, I have another problem to do, which again is very similar to one of your guys' homework problems. But I'd like to instead just like do something a little different that's not so math oriented in order to kind of mix things up here. I want to talk about Lenz's law. Just make a little bit of room here so I can have a little bit of theory stuff. So this is something I've already mentioned to you, but I have a bunch of examples of it here that I'd like to have you guys look at to kind of gain an understanding for what's happening with this. So let's talk about Lenz's law. That problem we did make any sense to you guys? Was it just really complicated? What do you guys think? Is it too easy? Is this stuff really simple for you guys? I don't know. Anyone out there? Just looking for feedback. It's really hard without. Seems average, not easy, not too easy. Okay. I hope when you finally do get to doing homework problems like this, this is somehow helpful to you. The biggest thing that I want to emphasize about this problem, the reason why I picked this problem, is because of this part right here. So that's the biggest thing I want to emphasize. I think you guys should be able to understand and figure out most of the rest on your own. I just know, like the first time I was doing problems like this, I just didn't really understand which area I was supposed to use right here. Like, because there's obviously two different areas. There's the area of the outer coil and there's the area of the inner coil. So just, it's the main reason I picked it, that one reason. So just keep that in mind when you are doing problems like this. I think that's one of the biggest places that you might get slipped up. Okay, Lenz's law. Lenz's law is really neat. This is something I really wish I could show you a demo. I probably can find one on the internet of this, but we have like at least 10 demonstrations about Lenz's law at the school. So it's unfortunate that I don't have them for you here. So Lenz's law basically states this. In the process of induction, Lenz's law describes the direction of the current that's induced. Okay, and what it basically comes from, or you know, is this negative sign that shows up in Faraday's law. This negative sign right here. That is Lenz's law, but it's difficult to understand what it means by just looking at an equation, and often you won't have an equation. So Lenz's law works like this. It says that when there's induced current, when current is induced, the direction of the induced current induced current is such to produce an induced magnetic field in a direction opposite to the change in flux. Okay, the induced current is such to produce an induced field in a direction opposite to the change in flux. I'll give you some really simple examples of this. We're going to look at a lot of examples of this here. Let me just give you a really basic one. So suppose that I have, let's say that I have a ring. How do I want to draw this? I guess I want to draw it kind of like, I think I could do something like this. Suppose I have a ring that's shaped kind of like this. And I need to erase just a couple lines here. So I want to erase, let's see, I want it to be, this is the front, so I need to erase this one. So we've got this loop, or a ring. I don't know if I'm going to be able to erase that part very well, kind of. So we've got this ring, right? Oh, I shouldn't have actually erased this part in the middle. I'm so bad at this. Should I have? Oh man, I don't know if I even want to draw this at this point. No, yeah, I should have just done this. I should have just gone like, draw a line from here to here, and draw a line from here to here. That kind of does it, actually. Yeah, that's fine. So suppose I have this ring such that this is like the front right here. Just say like this side is the... Oh man, this is like an optical illusion now that I look at this. All right, we're not drawing this. We're gonna use an example from one of these things over here. Let's just go straight to it. Not that one. This is the one that I put down here. Sorry, a little disorganized regarding this. Let's just do this one by one. That's the best way to do it, because every one of these examples will help you to understand what this thing says. Let's look at this first picture right here. So the first picture, I'll just draw a little bigger so you can see what's going on, and then you'll get the hang of like what's happening here. The first picture here, let's call this one number 1. You have a ring, okay? And then in that region, you have a magnetic field that comes out of the page. So that's B. Right? And it says B decreases, okay? The magnetic field decreases. The direction of the induced current has to be such that it produces a magnetic field in a direction opposite to the change in flux. So if your magnetic field decreases, right, what that means is that you're going to get an induced magnetic field in your ring that has to point opposite to the direction. So this is going to be the direction of B induced, opposite to the fact that it's decreasing, okay? Magnetic field decreases. the induced magnetic field is going to point in the same direction. I don't know if that makes any sense. If the magnetic field increases, right? So this is like number 2 right here. This is number 1. Number 2, if you have the exact same situation, okay, but instead what you have is, here, we'll just copy this and erase one thing. And just say, okay, now what's going to change is that the induced magnetic field is now, so in this case, the first one, right, B is decreasing. In the second case, B is increasing, okay? If B is increasing, that means that the induced magnetic field has to point in a direction opposite change in flux. So the flux is increasing out of the board, and that means that the induced magnetic field has to point into the board. Does that make sense? When the magnetic flux is, when the magnetic flux is decreasing, yeah, field is decreasing, therefore the flux through the ring is decreasing, right? The flux is decreasing, so the magnetic field that's induced has to point in the same direction. When the magnetic flux is increasing, you get an induced magnetic field in the opposite direction. That's it. That's what Lenz's law is. Does that make sense to you guys? What I'm going to have you guys do is to practice and try these. We're going to do 2 more. I'm going to tell you what the answer to each of these is, but the question here in all of these is basically what's the direction of the induced current? And as long as you know the direction of the induced magnetic field, you should be able to easily find the direction of the induced current. So like number 1 right here, what's the direction of the induced current going to be? Is it going to be clockwise or counterclockwise? If the magnetic field induced in the ring points out of the page, what do you guys think? Yeah, this way, right? That's I induced. And on this one, you get I induced the opposite way, right? So here's how I do these problems. This requires you to use your right hand, so you can put down your pencil for a second. Whatever screen you're looking at, or phone or whatever, if we look at this first problem that we did right here, okay? The first thing you do is you point your thumb in the direction. I'm going to actually write these things down because I think it helps to write these down. The first thing you do is you point the thumb, your right hand thumb, okay, that's step 1. You point your right thumb in the direction of the external field. So in this case, for number 1, the external field is the green one, right? The external field is the green one. And you just point your thumb in the direction of that, which in this case points out of the board, right? So you basically just put your thumb on the screen pointing out of the board. The second step is the flux decreasing? If so, then the direction your thumb points is the same as the direction of the induced field. And then the other question is the flux increasing? And if so, the induced field is going to be in the opposite direction as your thumb. So in this case, it's going to be same. Whoops. Same. In this case, it's going to be opposite. That's it. That's Lenz's law. You point your thumb, right thumb, in the direction of the external field. If the flux is decreasing, then the induced field is in the same direction as your thumb. That's like this one, right? And if it's increasing, the induced field is in the opposite direction of your thumb. You just flip your thumb around. And then the fingers of your right hand, the reason why you do this with your thumb, the fingers of your right hand are going to sweep out the direction of the current. Does that make sense? That's Lenz's law. That is it right there. It's kind of a way to, Now there's a couple. Does anyone have any questions? What's up? So remember what flux is, right? So just to remind you, there's 3 ways that flux can change, right? So flux is given by this expression here, right? Magnetic field times area times the cosine of the angle between the two of them, right? So one way that you can increase flux is just by changing a magnetic field, right? If magnetic field goes up, flux increases. It's that simple, right? If the area of the loop were to grow, the flux would increase. If the area of the loop were to get smaller, the flux would decrease. You could also have a situation where you could have like a coil, and that coil could basically be placed inside of a magnetic field, but let's say that the magnetic field was pointing kind of in this direction, so that it was basically parallel to our loop, okay? But then if that same loop was rotated to a position like this, where the flux has grown, right? So you basically take it and you put it parallel with the field, and then you rotate it from parallel to perpendicular with the field. That's also an increase in flux, right? Would you agree with that? Yeah. Okay, so any of those things are ways that flux can increase. Either magnetic field increases in the region, the area increases, or the angle changes somehow. Great question. So I'm just going to keep using green for external field, and I'm going to say here that when I have a magnet like this, we're just going to say that the direction of the magnetic field is pointing like this, okay? So in this problem, it says the magnet moves as shown. Which way does the current flow on the front of the coil? Like the front of the coil here. So you guys tell me, what's happening in this problem? If this magnet is, this is like a velocity, okay? It's moved to the left, right? If this magnet is pulled away, right? What happens to the flux through this coil right here? What's up? What did you say? I didn't hear what you said. Yeah, right. The magnet gets farther away, so it's decreasing, right? So according to that, then, what should the direction of the induced magnetic fields inside of our little coil right here be? Same direction or opposite? Same direction, exactly. So now it's going to get kind of tight in here, but this is going to be the direction of the induced magnetic field, right? And if I tell you that, can you guys tell me what's the direction of the current in the front here? Does it go up or down? You just point your thumbs in the direction of the field, right? And then wrap your fingers around. What way does your hand wrap? Does it wrap upwards or does it wrap this way? Yeah, so this is going to have a current that's going to flow like that, right? Does that make sense? Do you guys understand? What I want you to do is to try the rest of these, actually. They're all very similar, right? But you should be able to figure them all out. I have the answers over here to the right as well, but I'd love to see you guys like try to answer them all before I show the answers. Do you guys want to try it? Try to solve the rest of these? Maybe just as an example, we solved this one too. What do you guys think? For this one right here, what's the direction of the external field? External field is going to be like this, right? But now the magnet has a velocity towards the thing, right? So the induced field has to be, what, opposite, right? So now the induced field's going to come out this side. And to have the induced field come out this side, you have to have a current that goes this way, right?
Can I look at how you wrote Lenz's law?
Oh, yeah, sure. One more, it could go up just a little bit, right? The direction of the induced current is such to produce an induced magnetic field in a direction opposite of the change in flux. I personally, in my brain, this is how I do it, but I know that there's probably lots of people that have other ways of doing it. So just whatever way makes this statement up here makes sense to you. It's kind of cryptic, but yeah. Okay, I would love for you guys to spend, like, I don't know how long it would take to do all of these. But there is some similarity to these here. So give all these a try. There's what, 12 more, or sorry, 16 more, and see if you can get an answer for all of them, and then we can look at the answers afterwards. And I'll give you guys like, I don't know, 10 minutes? Is that enough time? So look at each one of these, try for yourself to figure out which way you think it's going. I'll be right here. Feel free to ask questions if you want to, but take 10 minutes to answer these. Who has changed their name to Asmongold? That's funny. Oh, that's Matt, Mina. Right on. Sure, I'm back. Was there a question? I heard it. I was getting water. I'll tell you what the answers are going to look like, actually. So this one, I'll put them up here. The first one is going to be like, here, I can write it like this. Actually, I erased all the answers out of here. So the first one is going to be counterclockwise, right? So I would write CCW. But I'm pretty sure that whoever wrote this up, instead of using, oh, that looks bad. It's hard to see what it says. So this is going to be counterclockwise, right? Or you could just draw it like this if you want to, right? Oh, which one did I do? Oh, I did 2. This is the one I did here, right? This one is going to be clockwise. But I think what you're going to see over there is it's going to say ACW for anti-clockwise. Because that's just another way to say the same thing. So you write CCW, ACW, or you draw like this, or you just do like this. I think this is just as easy. Just draw the direction if you want to, you know? And then this one is going to be, the answer for this one's going to be up, and the answer for this one's going to be down. That's the kind of answers you're going to expect if you want to have a quick way to... Oh, sure, I'll just zoom out. I'm kind of worried about zooming out because it might. Is that enough? Can you see everything now? Okay. Okay. I hope that was enough time for you to at least think about them. I'm going to briefly go through each one before we take a break here. I don't know. Do you guys want to just say really quickly, what did you get for this one right here? B increases. What's the direction of the field? Or the current? Counterclockwise, right? So you point your thumb into the board, but then it says increases, you flip the direction of your thumb, so this one has to be, oh, let's use purple. That shows up better. This one's gonna have to be this direction, or yeah, CCW. We did both of these. Here, B increases, so just compared to the one above, it has to be opposite. For this one, the magnet moves as shown. This is your external field. I guess we're using green for that. So the external field now goes this way. It's going towards it, so the induced magnetic field has to go the other way. The only way for the induced magnetic field to go the opposite direction is for the current to flow this way. Right? Let's see, up. Yep. This is going to be the direction of the current. This one, the magnet moves away. The external field goes this way. So if the external field points like that, then the direction of the current has to produce a magnetic field, since it's moving away, that goes in the same direction. I'll stop for a second because I answered like 4 of them. Did those 4 make sense to you? We did this one, this one, this one, this one. Or do you guys get the same answers, I guess I should say? So this would be CW. This would obviously be up. This would also be up. Everyone agree? And the rest of these are just kind of a repetition of the same kind of thing. So I'm just going to pull... Wait, are they all copies? Each line is a copy? So we've already answered all of them, haven't we?
2, second part of 2, I think it's what I got.
Yeah, I just made the assumption, for some reason, when I looked at this from above to below, that, yeah, you're right. This is wrong. This one's wrong, I'm sorry. I made the assumption, like, these are the same. They're exactly the same, aren't they? They're just kind of mix and matching. Like, yeah, okay. So this is the exact same as the one above, isn't it? It's like this. Right? So all the answers for these are right here. And what I'm going to do is I'm just going to put them upright like here, so you can see what the answers are. And then we're just going to take a break, so you can compare the answers you got. And I'll put them side by side, I think. Oh, that's not going to work very well because of what I did. Let me, here. What we'll have to do is go like this. That. And I should be able to move all this stuff down here. I may have missed 1 or 2 of them. But, yeah. Yeah, this one, this one, this one. No. Increases, 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 decreases, decreases. Okay. It's a lot of similarity, but... Okay, we're going to take a break now, and then we're going to come back and talk about another Newton's or Faraday's law problem. Break until what? 55 or 305, I think. Yeah. Okay. Oh, I just realized I've been recording this whole time. I should have stopped it.